Hello, and welcome to an analysis walkthrough video focused on variant calling of next-generation sequencing reads. This is included as part of the Biodata Catalyst powered by 7Bridges onboarding lesson. While watching this video, please keep in mind two key concepts. The first is that a typical researcher flow on a 7Bridges platform involves four steps: project creation, adding data files, staging apps, and executing analysis tasks. The second key concept is that analysis outputs can be viewed multiple ways without having to download the files and moving them out of the Biodata Catalyst ecosystem. At the end of the video, you will be able to run a basic analysis that can be used as a template for your own work. You'll be able to run an app from the public apps gallery, view the stats and logs of a running or completed analysis, and ask for support directly from the task screen without even having to send an email. Specifically, we are going to run the GATK haplotype caller on a 1000 genomes CRAN file. Haplotype caller, developed by the Broad, is a standard processing pipeline to call variants from next-generation sequencing reads. We are focusing on using a 1000 genomes CRAN file because it is an open dataset that is great for testing and training. It is hosted and available to all members of Biodata Catalyst. Additionally, it does not require specific dbGaP permissions to access the files. Let's get started. The next screen you will see is my platform dashboard, as I am already logged in to Biodata Catalyst powered by 7Bridges. Okay, so I'm already logged on to Biodata Catalyst powered by 7Bridges, and I'm already in a project I made for this demonstration called Analysis Walkthrough Variant Calling. Reminder, you can watch the previous module videos on project creation and on using the data browser to understand how I created this project. So far in the project, we have files that we added from the data browser. In particular, these are open access, hence the open lock here, 1000 genomes files. And the way the data browser works is you build a query, and I simply search for all CRAN files that are available, and it's giving us a very large set of CRAN files, but that's okay because we are not being charged for this storage. It's still, all this data still remains on NHLBI controlled buckets, and therefore we can link the data to our project and not worry about additional storage. So we have all the CRAM and the CRAM indexes as well. So our goal here is to do some variant calling on these open CRAM files. So the first thing we want to do is go to the public gallery. So in particular, the workflows in tools section of the public gallery. So we'll click on that. And we have the front page here, but let's click on Browse. We want to find a very particular pipeline that's very popular. It's part of the Genome Analysis Toolkit, so I'll type in GATK, and which still gives us many options here. But I know that I'm looking for best practices for germline SNP, so it just happens to be the first one. But just double check that your pipeline that you found says this: GATK Broad Best Practice Germline SNPs and Indel Variant Calling version 4.1. So all the apps give a preview of the workflow here. So this is starting with haplotype caller. So the inputs have to be already aligned to files. But you can read more about this. It gives you a description, common use cases, benchmarking. You can actually run this from a Python API client if you wanted to. Down here at the bottom, it gives you the required input. So we'll need the AmSam or CRAN file. So we have the 1000 genome CRAN files. We'll need some intervals. So in either VCF or interval list format. So more on that later. And then we'll need a FASTA file. So we have the cram files, and we're going to talk about these next types of files in a moment. The output will be a VCF file of the called variants. So when you're ready, click copy. Under the More Actions button, you copy it to your project. So I have this project already created, like I showed you. And then you can click this this link at the top here. It says the app has been copied to your project. You click this here, and it takes you to the Apps tab of your analysis walkthrough variant calling project. And you'll see that we have the one app that we need to focus on. And there is a copy icon here. That means that it's linked back to the public apps gallery. So this is not a new app that we created. This is one that we copied from the apps gallery. Okay, so remember, we need to get some reference files. So a great place to do that is still back in the public gallery, but go to the files section. You're here in the public files section of the public gallery. And this is a great place to find test data as well as reference files. And these are all hosted by 7bridges, so you don't need to pay for storage, even if you link these to your project. So I know from reading the GATK best practice workflow card that I need to find some FASTA files, in particular a reference. So I'm just going to type in FASTA, which is going to immediately search through the file name. And I have two good ones here. These are both tagged with Broad, and I've used these in the past, Homo sapiens assembly 38.fasta. So this is the FASTA and the FASTA index. So I'm going to go ahead and copy those to our project. And it gives us a indication that they're copied. Remember, these are actually being linked. It's not, when you're using cloud object storage, you're not necessarily making a copy of the file. You're just linking back to the 7bridges bucket. So it's very efficient. In addition, we need an interval. So there is a few different options here. We have the whole genome HC38 chromosome intervals, but I also made and published a chromosome 22 only calling region. And let's go ahead and just use the chromosome 22 because we're just testing how to run a workflow. But if you want, later on, you could go ahead and use the entire genome to call all the intervals to call variants. So we have our interval file. We're going to copy this to our project, and we'll be ready to go. So it gives us a link here, or rather a indication there. So let's go back to analysis work walkthrough, and let's just verify that the files are there. So we have the call the crams, all the cram indexes, and then we have the FASTA file and the interval list. So these are the files which we just copied. By the way, if you ever need to delete a file, you can do that as well. I accidentally copied, looks like, 2 indexes here. So I'll delete that one. And once again, it's not actually deleting the file from the 7bridges bucket, it's just removing the link from your project. So we have these here. So we're ready to run. So if we go to the Apps tab, we'll see our workflow that we already copied before. We're going to click Run on the right side. And here, actually, this is a feature of CWL. It can add suggested files. And that's part of the CWL code, which the developers on 7bridges have added. It already knows that we have Homo sapien assembly 38.fasta, but it's also suggesting to add this. I'm going to say don't copy because we just wanted to call on one chromosome. So look what it already filled in Homo sapien assembly 38.fasta for us, which was very nice. But we still need calling intervals and input alignments. So let's select the calling interval, and it knows that calling intervals should be in VCF or interval list format. So I'm going to use the file picker to pick the appropriate file. And we still need to fill in alignments. So the alignment could be any of the 3,202 CRAM files, which we linked from the data browser. I'm just going to pick a couple to demonstrate. And in fact, why don't we choose some of the smaller ones so we can sort going ascending. So I can pick the two smaller ones, NA 12753 and NA 18911. So I'll call variants on both of these because I want to demonstrate batching. So you can actually put these in the same workflow, which will be fine. But if you want to run them in separate cloud instances, you can turn on batching. And sometimes this actually is required to get better performance. I'm going to choose batch by file. So this is actually going to run 2 tasks, one for each of the files. And I do not believe we need to specify any parameters. So in the middle, we have app settings. These are completely optional, so I'll leave it at the default. And we are ready to run. So I'm going to click run. And it's going to let us know that we're going to run 2 tasks, one for each input CRAM file. And that's okay. So if I hit refresh, it actually has the parent task and has 2 child tasks under it. So these are if I click on one of them, it's showing that it was queued up for a moment, and now it's going to run through each of the 3 steps. Remember, the 3 steps are working with the interval list, running GATK haplotype caller, and then merging the intervals into a single VCF. And it will do that for each of these. Back on our tasks tab, we see that our batch task of GATK Broad Best Practice Germline SNPs and indel calling has completed. We can click on the task name, which gives us the parent task, and then we see that the 2 completed child tasks are right under. So I'll just show you what one of them looks like. So this is what a completed task looks like. You get all this great information, and this speaks to the sort of reproducibility of the platform. So this will always be part of our project. So we have this record of the inputs, the app settings. So even though we didn't specify any unique app settings, it has all these default settings that are displayed for us here. And of course, we have the output, which is NA 12753.3.merge.vcf. I want to point out something else, which is interesting. Remember, hosted data you're not charged for. So in particular, these large CRAMs are hosted by NHLBI Biodata Catalyst, I should say, and it's using a DRS technology. So really, this is indicating that it's pointing to a file that's on a DRS server. And that's a GA4GH standard if you want to research more about that. Okay, to see the outputs, we can click on the merge.vcf. Now, a preview of VCFs and other and flat files such as CSV, TXT will normally pop up here if it's 10 megabytes or smaller. That said, you should know that if it's a text file, you can always click on the raw view. And we see that this is a well-formatted VCF. It's got a header here, and then we can sort of scroll down and see the variants. Now, you do not need to download data to your computer to view it. So you get a nice preview here, but interactive analysis and exploration, a great way to do that is to use Data Studio, which is right next to your task tab. Data Studio is how you could launch R or Jupyter Lab or SAS Studio and have access to all the files in your project and interact with data sets in real time. One more thing I want to show you is for any task, you have log files that are saved forever, and those are under the view stats and logs. I also want to mention that if we needed any support here, we could easily click Get Support, and we have the option of inviting a team member to our project to help us, or just have them look at the error message, and they'll get back to us if there was an error with the email address that we provided when we registered for the platform. Lastly, I just want to show you what happens when you click on the View Stats and Logs. See this nice timeline, and this is really for more advanced users, but I just want to let you know that it's available. This shows you each task, and rather each job for each of the different steps of the workflow. You can see instance metrics, which will show you over time how much CPU, how much RAM, how much storage, and the input, output, and load average. This is really great if you're wanting to benchmark and optimize your tools. That's really helpful information. Also, you have a View Stats and View Logs button, which each step in the process will have a subdirectory here where we could see the standard out, job.error.log, job.tree.log, and the actual command line that was run. So if you ever need any of that for your records. And that's about it for the demonstration. Okay, let's recap what we just learned. We demonstrated the basic researcher analysis flow by running haplotype caller on a 1000 genomes CRAM file. Remember, the basic flow is project creation, adding files, staging your apps, and executing an analysis task. As a bonus knowledge check, think about running haplotype caller on all 23 chromosomes. What would you need to change to make this work? This concludes this video, and thank you for your attention. If you are following the onboarding lesson, I recommend watching the Billing Groups and Pilot Funding module next. After that, try the onboarding lesson exercise in the last video to challenge yourself and to test your knowledge. See you in the next video.